we go. This is why, because it's really, this is a pre-calculus idea, which means easy. Are you ready? Easy.
I don't get it.
No, just deny.
We'll get to the homework. I think this will be, I think I'll get through enough. I don't know. Let's just roll with it. We'll see what happens. I don't know where the period will take us. You know what I mean? Let's just go with it. Okay, so hyperbolic trigonometry is something that you need to go before you go to college. If you're going to be a math or science person, generally college level math classes require you to know hyperbolic trig. Kind of useful in real life, especially in some physics problems and engineering problems. So that's why it needs to be taught. It's not an AP test, but I don't want you to go and your first semester be in Calc 3 and be next to a kid who took Calc 2 at the college and be at a disadvantage because they've seen this and you haven't. So I want to make sure that you've seen this. It should be pretty basic level, just introductory level, right? So here it goes. There is this idea of hyperbolic trig, and it really doesn't have anything to do with triangles. There's nothing about an opposite side or adjacent side. There's not even an angle. There's not even a theta. Instead, hyperbolic trig is actually forms of exponential combinations. If, for example, you took e to the x, subtracted e to the negative x, and divided by 2, then you get what's called the hyperbolic sign. Now, I think I already put this in the box for you, yeah? It's fun to say the hyperbolic sign, but most people would say that is sinh of x, yeah? If you were to add e to the x and e to the negative x over 2, that's the hyperbolic cosine, which is cosh. Okay? Now, why would you want to add those e's, and why would you go and divide by 2? We'll come to that shortly, but a better question right now is, why do they even call it trig if it has nothing to do with drawing a triangle and finding angles and sides? Why do they even call it hyperbolic trig? Because when you actually combine these, it mirrors a lot of trig ideas. For example, if you were to take this guy squared and that guy squared and play with it a little, you get an identity. Now, it's not normal trig Pythagorean identity. Sine squared plus cosine squared is 1. It's got a negative in there, which you'll see when we go to show this. So if I said prove this is true, prove this, then I would suggest you start by saying, all right, I'll start with this, that which you tell me. And just like any identity, you usually work the complicated side and make it look like the simple side. So, what can I put in place of cosh? E to the x plus e to the negative x all over 2. Should we make 2 changes at once and therefore leave everybody following us in the dust, or should we go one change at a time?
We should leave them in the dust.
Leave them in the dust, you say. All right, forget those fools. One change at a time. Okay. All right, great. I still don't think it's self-evident why that equals 1. I don't think even the most biggest genius in the world could say, oh yeah, that's definitely 1. I mean, come on, that's not there yet. Do you agree? So let's continue further. How can we clean this bad boy up? Square those. Okay, so this squared is, should I write it out, or can we square it mentally? What do you think? Write it out. E to the x plus e to the negative x over 2. E to the x plus e to the negative x over 2 minus e to the x minus e to the negative x over 2. E to the x minus e to the negative x over 2. Okay. In the first, I think I'll handle the denominator. 4. You handle the numerator.
Do we know it out loud?
E to the 2x
plus 2 e to the 0.
2e to the 0, I agree. plus
e to the negative 2x.
e to the negative 2x, all right? Minus, I'm going to put this in parentheses. Actually, I guess I don't need to put it in parentheses. It's going to be a fraction anyways. All right, I'll do again. Over 4.
Thank you.
You're welcome.
E to the 2x.
E to the 2x
E to the negative 2x.
minus
E to the negative
2e to the 0
Okay.
plus
Plus e to the negative.
a to the e to the negative 2x. Okay? Alrighty, let's break this up into little pieces, shall we? So I've got your e to the 2x over 4 plus, what's 2e to the 0 over 4? 1/2 plus e to the negative 2x over 4 minus, now I'm going to definitely need parentheses, so I distribute the negative, e to the 2x over 4 minus 1/2 plus e to the negative 2x over 4. Oh, wait.
Right.
Hold on, I just can't read that.
Oh, I didn't think I was writing that fast myself, but okay. Thank you very much. E to 2x over 4 subtracts away, yes?
All right.
1/2 minus negative 1/2 is,
0, 1. No, that's 1.
okay? And e to the negative 2x over 4 minus e to the negative 2x over 4 is 0. So we get 1 equals 1. I think we'll agree that's all true, yes?
Right.
So, one reason to call it hyperbolic trigonometry instead of hyperbolic exponentials is because it has an identity. All right? Another idea that makes it like, oops, you saw that? Another connection / similarity here. All right? If you start with sine squared plus cosine squared equals 1 and is normal in the unit circle, when you talk the unit circle, isn't the hypotenuse 1?
Yes.
And so, isn't cosine just adjacent over hypotenuse? Cosine is x, and sine is just what? Yes?
Yes.
Okay. So, that's why in trig, sine squared plus cosine squared is 1. It's because if I say that sine squared is the same as y squared, and cosine squared is the same as x squared, I get just a plain old circle. And it doesn't matter what the angle is. The x squared and the y squared always equal 1, whatever the triangle looks like. Follow?
Right.
Now, by the same token, if I let cosh equal x and sinh equal y, then I would replace the main identity with, instead of cosh squared, I could say, well, that's the same as x squared, and sinh squared is y squared equals 1. Now that's not a unit circle, that's actually a unit hyperbola. A hyperbola with if you called it that, of 1. So they have kind of similar graphs in that instead of many triangles making a circle, you're talking many of these exponentials making a unit hyperbola. Continuing on. Or not. Is this the next thing in your notes?
No. We skipped the reciprocals exist.
Oh, shucks. Are you sure?
Pretty sure.
Alrighty then. Give me 1 minute. You just sit there and look pretty for a second. I'll be
I disagree.
All right. Okay. Now, just like in trig, there are 4 other trig functions that come from the first 2. So this guy is the same as sinh over cosh. You could also say it's e to the x minus e to the negative x over e to the x plus e to the negative x. The over 2's go away. And students say, well, so do you pronounce that? How do you reckon you pronounce it? As far as I know, there is no such thing you would say hyperbolic tangent. Sorry. Hyperbolic.
I'm calling it.
You can call it whatever you want. Tangent. Hyperbolic cotangent is cosh over sinh, or I guess e to the x plus e to the negative x over e to the x minus e to the negative x.
Take the
And that's not cough.
Yes, it is.
It's hyperbolic cotangent.
You can't stop this now.
All right. So
You were going-
hyperbolic secant is 1 over cosh. You could say 2 or such. 2 over e to the x plus e to the negative x. And the hyperbolic cosecant is
Sech.
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 Cosech? Cosech? See, it's just ridiculous. 2 over or 2 over 6. Okay? Furthermore, there's also inverse cinch, inverse cosh, inverse hyperbolic tangent, inverse hyperbolic cotangent, and so on.
I'm confused.
Yes?
Why is the secant one and the cosecant one, why are they different?
Why are they
Like,
different? What
one
do
of
you mean?
them is 1 over cosh, but the
Oh,
other one is...
this should be 1.
Okay.
Okay, good call. Okay? All right, in your calculator, get out your calculator, please, or any calculator.
I know where to find them. It's just type H.
Yeah. Does anybody have an 84? You all have iron.
We all have the same.
Hey. All right. The easiest way to go is just to get the normal trig function and then just go back and scroll back and put an h in. So I will show you what I mean. Okay, so you get 3.628. Okay. Okay, what about inverse hyperbolic or inverse cinch of 2?
That ain't right.
Okay, do you get 1.443? You did? Oh, trickster. 1.443 or 1.444, yeah? Okay. That's good. Is this the next thing? Okay. Let's talk graphs. Yes, these have graphs, and they're really cool. Okay? You should be able to do this without a calculator. So, think e to the x over 2. What would e to the x over 2 look like?
Slightly less.
Okay? What would the y-intercept be?
1/2.
1/2. And then it would be slightly less growing. It's a vertical squish, yes?
Right.
Okay, what about e to the negative x over 2, which will be dotted? E to, does this say e to the x over 2? Oh, sorry, I have a typo there. E to the negative x over 2. What do you get when you put a negative on the x? Okay, so it would still be at 1/2 and it would decay. All right, now then, let's consider the combinations that make cinch and cosh. So for cinch, we're going to take the blue graph, e to the positive x over 2, and subtract away or take the difference between that and the y values of the dotted graph. So over here, if I take the blue graph minus the red graph, what do I get? Positives or negatives? Negatives. And will they be getting bigger and bigger, or the difference be getting bigger and bigger, or smaller and smaller? Bigger and bigger. So it'll be negatives here. And what about at 0? They're both 1/2. So 1/2 minus 1/2 is
0.
0. Oops. And What about on the right side? We're taking blue minus red, so bigger numbers minus smaller. They'll be bigger and getting bigger, yeah?
Yeah.
So it looks like that. Like a cube,
Like a tangent.
like a cube. Quicker growing or slower growing?
Quicker.
Exponential. Quicker. Much quicker growing. Growth because it's exponential. It is off. Okay? Cool. What about cosh then? Look again at this side. This time your cosh is adding the two graphs. So on this side you're taking big positives plus little positives. You get
Bigger.
big positives even a little bigger than the red. So it'll be bigger at 0. When x is 0, what do you get?
1.
1, because you get a half plus a half. Or they're both 1, or both 1 in the top, 1 plus 1 over 2 is 1, either way. And what about on the right side? Big positive plus little positive is?
Bigger.
A little bigger positive. So, hi. Thanks, sir. I think they're back there. Okay, so you can see that cosh is, what? It's even. Yes, it's an even function, just like cosine is. Go figure. So many similarities. Derivatives and stuff we'll talk about in a second, but it's an even function. Now this curve actually is the most real life application of hyperbolic trig. So if I were to, well, I'll just go here. So if I were to hang this from two poles at the same height, what kind of shape?
Parabola.
Feels like parabola, right? But no matter how good of a parabola maker you are, you could not fit a parabola to this. It's not a parabola. There is no parabola that could match this at every point. Just doesn't exist. You know, it looks like a parabola, but it's actually it's a Koch curve. Okay, any slack cable is modeled by a Koch curve. The same with arch. People think it's a parabola. It's a Koch curve. It's hyperbolic cosine. Yeah. So, if you ever, has anybody ever been to Barcelona?
No.
Sagrada Familia. It's like the most amazing church ever. But the designer of the church is famous for a lot of things, but most of all, it's arches. It's just got arches all the way throughout. And if you go there, it shows how he designed the model. So he hung it from the ceiling, and he would hang a cable and put a little weight on it so there would be a slack cable here, right? And then he would do it from this side, and then he would hang another one from those. And so it had all these hanging things, look kind of like a chandelier. But to see what it was actually going to look like, he then put a mirror on the ground, so that when you looked in the mirror in the ground, you got to kind of see how it was going to look going up. It's so cool. If you ever go to Spain, go to Barcelona. It's famous for its architecture, the Modernisme movement. It's so cool, but it has this idea of slack cables all throughout the architecture. It's amazing. Go to this idea here. Just like in trig, we already did this. What the heck, are these out of order? Is it just deja vu, right? All right, so let's go to limits. Would you do these limits for me, please? It does say you can use end behavior, so you don't necessarily have to use L'Hopital. ¿Listos? I wish I had reviewed this before, because now I can't remember how to do it. Think my way through it here. Think on the fly, baby. Part of teaching. So I didn't quite know what to make out of that, so I felt like it would be easier, or I could do a nice cleanup step if I multiply top and bottom by e to the x. If I do that, then isn't it e to the 2x minus just straight up 1? Are you with me? Are you with me? Over e to the x, 2x plus straight up 1. That might be a little cleaner. As x gets infinitely large, these obviously mean nothing, and it approaches 1. Okay? Now the question is, what about at the negative side? Will the negative side be any different, or will it also approach 1? So let's think about this. If x goes to negative infinity, then doesn't this go e to the negative infinity, which approaches 0. So this is like 0, that's like 0, so now it approaches negative 1. Now that's why when you say end behavior and horizontal asymptotes, you really have to look at both sides, because it is possible you get two totally different horizontal asymptotes. If you were to do this, it would look something like, what about a 0? What is it equal to? Maybe we should look at sinh over cosh. What's sinh over cosh at 0? 0 over 1, so zip. All right, give me out 0. So it's actually looking something like. Okay. Differentiate and integrate. Why did I split that objective from the? Do you have something next, or does it just go nothing? Do you have a blank space now?
No.
You have actual things? Oh, super. That's great.
Differentiate and integrate hyperbolic space.
I already got that. Thank you. What else do I have?
Oh, I'm sorry.
Okay, here we go. Would you? Geez, I guess we're just doing this whole thing together, eh? Yeah, I should print off set 90 so you have some homework. I want you to be bored this weekend. Okay. All right. Would you find the derivative of sinh using the exponential forms, please? Go. Find the derivative of sinh and the derivative of cosh. Oh, what? Are we done?
No.
So the derivative of sinh is cosh. And the derivative of cosh, not negative sinh? Just sinh, not negative sinh. So it is not like normal trig. It is sinh, not negative sinh.
Can we fix it?
No, it is what it is. You also fudge your results in your labs too? And say, let's make it better. No, never fudge your data. Okay, would you find the other 4 derivatives then? Find the derivatives of the others. That time you don't have to do the exponentials. You can use sinh and cosh to find the derivatives of the other 4. Low. Yes. Oh, that's somebody's semester. Okay. What about the derivative of hyperbolic tangent? Or tangent? Cosh. 1 over cosh squared. So hyperbolic secant squared or sec. The top is an identity. Cosh squared minus sec squared is the main identity of equal one. Yeah. Hyperbolic cosecant or negative hyperbolic cosecant. This time you get an opposite sign in the top, so you have to use the opposite of the identity, so it's negative hyperbolic cosecant. Wait. Wait. Do you want to use quotient rule or chain rule? Chain rule, okay, so for negative first, that's negative first exponent, not negative first inverse, right? Negative sinh over cosh squared. How do you reckon we clean up negative sinh over cosh squared? Negative sine over cosh is sine over hyperbolic sine over hyperbolic cosine is hyperbolic tangent, and then we have a 1 over cosine still left, so that's a hyperbolic secant. So in this case, it feels like hyperbolic secant is negative tangent secant. And then we'll just do songs. So what about the last one? Cosecant, hyperbolic cosecant derivative is negative coth, which is not a thing. It's coth. Coth and 1 over sine. This is the hyperbolic cosecant. Okay, so obviously if they have derivatives, they have antiderivatives. What's the antiderivative of hyperbolic sine?
Hyperbolic cosine.
Hyperbolic cosine. What's the inverse or the antiderivative of hyperbolic or of cosh? Sinh. How do you reckon we do hyperbolic tangent? How do you do tangent? U sub, yeah, it's sinh over cosh with the u of cosh, so du is sinh So this is 1 over u du, and so our antiderivative of hyperbolic tangent is
The natural log of the absolute value
of
cos.
cos.
Whereas absolute value is not needed.
That's true. Absolute value is not needed. You're right. Absolute value is not necessary because cos is always positive. Good call. Okay.
Redemption.
What about
Redemption.
throw this? I think you're expected to throw this in your calculator. That's what that approximation means, just to see if you can integrate that. Throw it in your calculator and tell me what you get.
Why is C to the top? It's called. It's called. No, it's no longer. It's Caltech and Thomas. It's love. It's
Number
the
3.762.
I feel wrong.
Okay.
I got 2,646.
I definitely did not get that. I got
2,000.
Are you radiant?
I didn't agree.
So
It doesn't matter.
should radians matter?
No.
You can put in radians, put in degrees, you'll get the same thing. So it won't matter.
3 matters button pushing?
So because it's not based on angles, it's based on exponentials. So shift plus 2 to 2
You did push. Oh, I did call.
2
Cosh.
E
Not Kosh.
to
Kosh.
Don't you know the difference?
It's Kosh. It's not like Caltech.
off.
Caltech doesn't make a difference.
We're good? Hey, oh, you get the idea?
Just make it
Do it on cue.
No, no, no.
It's got one of the special white buttons.
What? I get 2.72. We good? Oh, okay. All right.
White buttons are scary.
Is that all?
Prejudiced against the black
that all?
buttons.
Yeah, that's it.
I see the white buttons are scary.
There's your homework. All right, let's go to the yellow, the gold sheet, and finish going over the gold.
Sacred buttons.
Do-do-do.
No. You don't need to get what there.
Okay, is this where we're at?
Hi.
Okay. All right, did we get through any of this yet? Did we get the tangent line equation? I think we got the tangent line equation, but not whether it's above or below. Yes? Okay, so what determines if a tangent line estimate is greater or less than the true value?
Concavity.
Concavity. Is it enough to say concave at the point of tangency, or do you have to say it's concave up from the point of tangency to the point you're looking?
From two.
So yeah, because here, if you say, hey, see, it's concave up at the point of tangency, and I'm estimating, well, what if you looked way over there? Are you going to be overestimating or underestimating anymore? Well, no, you're going to be overestimating. So it has to be concave up over the interval we're talking about. So in part B, you should be saying something like the second derivative is greater than 0 on the interval 1 to 1.1. So the tangent line, so the estimate is it concave up? Yeah. So if it's concave up, is the tangent line going to over or underestimate? So the estimate is less than the true value. You follow me? Okay, and then part C. Did you get y equals 1 over the square root of negative 2x squared plus 9/4? Oh, that's a pity. I guess it's decision time. Should we go through this? We still have 13 minutes, right? Okay, so let's go through this. Am I going to work with the first or the second derivative to get the particular solution?
First.
Okay, so let's start here. dy dx is xy cubed. Let's separate yield variables. So dy over y cubed equals x dx, right?
Right. Yes.
What is the antiderivative of y to the negative 3?
Negative 2 in the
Raise it by 1, divide by the new.
negative 2.
Y to the negative 2 over negative 2 equals x squared plus c. If we use the initial condition, like, what is it? What is it? 1, 2? X squared over 2, thank you. Using the initial condition 1, 2, doesn't that mean that 2 to the negative 2 over negative 2 equals 1/2 plus c? That's not very usable. What is 2 to the negative 2 over 2 like?
It's 1 over negative 8.
1 over negative 8 equals 1/2 plus c, so c is negative 1/8? Negative 5/8. Okay, negative 5/8. So now my equation is y to the negative second over negative 2 equals x squared over 2 minus 5/8, yeah?
Yes.
Okay, what then did you do? Did you deal with the y to the negative 2 or deal with the dividing by negative 2? Did you, let's move this first, shall we? Y to the negative 2 equals, when I multiply this by negative 2, I get negative x squared. When I multiply this by negative 2, I get positive 5 over 4. Do you agree with that? Okay? Here's where a common algebra or numeric mistake is made. True or false? True. If I take reciprocals, still true? Okay, so when you take reciprocals, you better doggone well be careful, because you can't just say reciprocal here, reciprocal there. It doesn't work that way. How can I work with it? If you take reciprocals and you have a sum, maybe it would be better to say I could add these together. Then if you flip them as one big fraction, is that true?
Yes.
That is true. So if you choose to say flip this side, flip that side, you best make this one big old fraction before you do so. So 1 over y squared is negative 4x squared plus 5 over 4, yay?
5.
Okay, now can I say, all right, then that means y squared is 4 over negative 4x squared plus 5? This matches what it's mathematically equivalent. All right, so y then is the positive or negative square root of that, yeah? Do you agree with that?
Yes.
All right, is that my answer? If they say find y equals f of x, then you want a single function. This is not a single function. This is two different y's when you put in an x. You can't do that. You have to say use this one. Now, if they tell me I'm supposed to get the point 2, 1, or is it 1, 2? If I'm supposed to get the point 1, 2, then surely when I put in an x of 1, it's got to be 4 over negative 4 plus 5. That's got to be, what do I choose? Positive or negative to get a positive 2 when I put in? I need to choose the positive side. So y is the positive of 4 over negative 4x squared plus 5. I must have dealt with the constants a little differently in the first one, but either way, you're good. You with me? Yeah. Okay. Let's go to the back side. So A, did you get something like a tangent line of y minus root 3 equals 2 over root 3x minus 1? Okay, did you get that for your approximation f of 1.2 is approximately y of 1.2, which is root 3 plus 2 root over root 3, 1.2 minus 1?
Yes.
I didn't do anything more, I just said there you go. Okay, B. That was B actually. There must have been a slope field problem. I left off A. C. Did you get a solution of y equals the square root of 2x squared plus 2x minus 1? Why are we getting these? What's going on here? Let's go through it, shall we? When you separate the variables, what did you get? You have dy dx equals x plus 1 over y. Separate the variables. Y dy equals x plus 1 dx. Okay, integrate. Equals. Okay, that's not the problem. So now let's put in the initial condition. It says use the point 1 root 3. Okay? So when I put in root 3 on the left, what do I get?
3 halves.
3 halves equals 1 half plus 1 plus c. So c is 3 halves. Yeah. Okay. So y squared over 2 equals x squared over 2 plus x and no c. Now what? Y squared is x squared. I have an error in there, so you don't have a 2x squared. Is that why you? Oh, I got a c of negative 1 half. Why did I get a c of negative 1 half? Oh, okay, so maybe you did this right. I have an error in my work. Maybe you're good. Maybe I'm dumb. Not even maybe. So do you agree with that?
Yes.
So y is plus or minus x squared plus 2x.
Positive.
But we choose,
Positive.
okay, in other words, for this to happen, we choose positive. And so it's x squared plus 2x squared rooted. Is that what you have?
Yes.
Oh, sorry, you're doing great. Good job. I'm doing bad. Is there another part? D. Did you get that f of 1.2 then? Now that you actually have the function, rather than use the tangent line to estimate, we can actually find what is f of 1.2. And f of 1.2, I got the square root of 4.32.
No.
Nope, my function was wrong, so that's going to be wrong. So feel like more like 1.44 plus 2.4. So more like the square root of 3.84. Okay, cool. Number 7 had a good piece in it, and then I screwed up. So if you felt like, what, this is breaking math, that's my bad. I do want to focus, I don't want to dump this all together. So this was a huge source of error on an AP free response a couple of years ago. Do you agree with my separating the variables?
Yeah.
Okay, so when you integrate the left, what is it? Is it natural log of 4 minus b?
Negative.
Negative natural log of 4 minus b. Now, if you're going to be mentally use something, you had a doggone well be good at it. What's u? 4 minus b. Then what's du? Negative 1 dB. You get a negative there. It is natural log, negative natural log of 4 minus b, not log of 4 minus b, negative log of 4 minus b equals 1/3 t plus c, yeah?
Yeah.
After that, if you put 4 in, so here b is 4, do you agree? So if you put 4 in, then all heck breaks loose, and my bad. Okay? So forget after that. Don't worry about the plus c and e after. I did want to integrate that though. For this, separate the variables, please. So this is here for a reason. What's the best way to deal with the 1/3? Leave it there or move it over? It's so much easier if you don't give a fraction, you make it full. It's so much easier for you in many cases. So 3b equals 4t minus
T squared over 2.
t squared over 2 plus c. After that, I got that c was 6. Did you agree with that? C is 6, and so b is 4/3 t minus t squared over 2 plus 2. Oui? T squared over 6. Oh yeah, sorry, 6. You're right. Okay. 3. What's this all about? Oh, I went the wrong way. Okay, 3. What'd you get? It is E. And 4. All right. Do we have enough time to go over the Newton's law of cooling real quick? That was a bit of a source and error. Did you divide to get the Newton's law of cooling problem okay? Or should we go over that? We did the part E in class, the getting the equation? No, I don't think we did. Okay, so the Newton's law of cooling part E, you've got dt dt equals K times temperature of the cake minus 70. I'm going to put the 70 in for the temperature of the room. It's easier to work with. You with me? Separate the variables. What do you get? dt over t minus 70 equals k dt. Integrate the left. Now that one's not a danger issue, so because the negative isn't on the t. So this is straight up log of t minus 70 equals kt plus c. You have an initial condition. You know that at time 0 the oven is 100 or 400, right? So the log of 330 equals 0 plus c. So c is the log of 330. Are you with me? So the log of t minus 70 equals kt plus log of 330. Students sometimes want to also use the other case now to find the k. I guess you can. Do you want to use the other case now to find the k, or rearrange it first and get the exponential, then find the k later? K now?
Yeah.
Okay, so if I use the other case, isn't the 300 then going to go for t, making that 260?
30, yeah.
Oh, yeah, sorry, it wasn't 330, it was 3, I thought it was 330, sorry. 230 equals, what, 4 minutes? 4k plus log of 330?
Yep.
So 4k equals, that would be a subtraction problem, but subtraction can be combined into a single log of, yeah, 230 over 330, yeah? So divide that by 4. Anyway, you start to see where we're coming from. Then you still have to solve, but that should be true. I want this today, please. I want this today. If you're done with 89, I want to in, fine. But it's not due today. Just this. Okay? Have a great, there's no homework, I guess. I'm sorry.
All right.
You feel terrible. Instead, your homework is to go see the play.
It's not for the Devil in Marching in the Street. No, that's not important. I'll go with one speed like 7 times.
Johnny put in 3 times in the play. Johnny 3 times in the play. The best of over here. There's a casting overtime. There's a plays.
Okay. Hey, Dr. Richard. I know something too. I think there's like writing a video.
I think he heard you. I thought I heard you. What is this? I don't know. I saw what this is.
Just to keep in mind.
You wanna know what's relationship? When I make it in a